Welcome everybody. So I wanted to make a quick little video for you on what you need to know in preparation for our first chapter in precalculus, functions. So what I did is I designed a couple questions and some problems to work through that's going to give you a good foundation just to kind of remind you on some of those essential skills and topics that we've learned in previous classes before we get into the functions unit for precalculus. So, just kind of look at, kind of go through this worksheet real quick. For number one, look at talking about domain and range and looking at determining if something is set of points are a function. Question number two, we're going to look at evaluating different types of functions. For question number three, we're going to look into solving quadratic equations. And question number four is going to be solving and graphing inequalities using the number line. Question number five is going to be simplifying different types of expressions. And then number six, we're going to talk about transformation. So this is not a complete list of everything you need to know to prepare for functions, because there's going to be a lot of things that as we work through the curriculum, are going to come up, and we'll address them at this time. But these are some of these essential kind of skills that I've kind of found that I feel is a good kind of refresh for students before they get deep into the function material for precalculus. So let's go ahead and get started with going through this work and seeing what everything was again. Of course, if you forgot it or it's been a while. So the first question states, determine if the set of points represents a function or not. If so, determine the domain and the range. So just a reminder that remember, the domain is the set of input values of a function, whereas the range is the set of output. A function is basically, the definition of a function is where you have an input that uniquely maps to only one output. So, you can think of these coordinate points here as x and y coordinates. Now, we could list the set of all the x coordinates, like this is an xy, that's an xy, and that's an xy. Well, when you write them as coordinate points, they're mapping to each other. That's like they are, these are connected. This x is with this y. This x is with that y. So every x can only uniquely go to a one y. So if you look at this, this x, 0 goes with 1, 3 goes with 5, -2 goes with 0, and -3 goes with -3. So it looks like every x uniquely maps to a y. So therefore, this is a function. So we can say, yes, it is a function. Now we need to remember what the domain and range are. Well, remember, the domain is the set of all x values, typically, or the set of all input values. So I'm just going to use D for domain, and I'm going to use a set here. So I'm just going to list the coordinate points, 0, 3, -2, and -3. Then the range here is going to be the set of all y values, or output values. So that's just going to be 1, 5, 0, and -3. All right. For the next one, what I'm going to do is I'm just going to go ahead and look at the list of the set of domain as well as the range before answering the question on domain and range. Because if I do the domain here, I get 1, -1, and 2 looks like it repeats. So that's kind of interesting because 2 goes to 1 and 2 goes to -1. Well, that doesn't work. That goes against our definition of domain and range here, because 1 maps to 1, -1 maps to 2, but 2 maps to 1 and -2. So you can see when values from the domain go to two different y values, it's not a function. So technically, we don't even have an understanding of a domain and a range. We don't even really need to include that. But I wanted to write out the domain, and I wanted to write out the potential domain and range so that you can see how this input value goes to two different output values. And just a quick reminder, remember that there's many different ways to represent a function. Points is one. We could do equations or graphs, or, mapping is another thing that we looked at. We're primarily going to be looking at equations and equations as well as graphs. But the point method is a good way just to kind of refresh some things, or at least our understanding domain and range. All right, so here I'm just going to kind of quickly go. 3 goes to 0, yep, and 1 goes to -2, okay. 2 goes to 0, all right, and then -2 goes to 3. Now, this one's kind of interesting. 3 goes to 0, and 2 goes to 0. That's fine. they can go to the same output. Like you can have two different inputs going to the same output. You just can't have the same this one input going to two different outputs. So therefore, this is a function, all right, because it uniquely only goes to one unique output. It doesn't go to different outputs. So therefore, I'm just going to list the domain as a set of all x values. So that's going to be 3, 1, 2, and -2. Now the range, there is a repetition, so we don't need to write it twice. 0 happens, occurs twice. We don't need to write it twice. We just need to write it once. -2, 0, and of course I read it twice. 3. And again, you can see that 3 goes to 0 and 2 goes to 0. But that's fine, as long as they go to 1. Each input domain cannot go to two different values, okay? So that was basically the good review for functions and relations, domain, and range. Now let's go and look into evaluating the following expression. So we're going to work into some different functions. Hopefully these are all functions that you have you've had some experience with, so I'm not going to spend too much time because anything we have difficulty with, we're going to do multiple examples of. Just remember, when we're looking to evaluate, that means we're looking for the value of the expression when x is equal to -1. And since x is equal to -1, that means we can replace x with -1. So that's basically all I'm going to do. I'm just going to rewrite each expression, and I'm going to use parentheses to represent me plugging in -1 in for x. Now, just be careful here, the double negative. So this is -3 minus a -1. So it's like, that's really adding a positive one. So I have -2. So that becomes a absolute value of -2. Remember, the absolute value is like the absolute distance from 0. So it's always positive. So therefore, this becomes -2 times 2, which is -4. So I'm just kind of working in through my step-by-step so you guys can, again, remember that's an absolute value, not the number 1. So you guys can see all of the math kind of going in from there. Here we have 3 times -1 squared minus 2 times -1 minus 4. Just remember, we square the -1, so don't multiply by 3 first. That's -1 squared, which is a positive 1, times 3. -2 times -1 is a positive 2, and then minus 4. So again, let's just work from left to right. 3 plus 2 is 5, minus 4 is 1. And the next one here kind of looks a little crazy. We have a radical square root as well as a squared. But that's okay. Just, kind of, again, plug it in and see what happens. So 5 minus -1 squared. So again, kind of like what we did over here, but again, it's important just to kind of follow the order of operations. Remember, when you have, a function inside of another function, work from the inside, innermost function. So in this case, we'd have -1 squared, which is going to be a positive 1. So then 5 minus 1, positive 1, is 4, which then is going to equal, let's just do this. So this will be 5 minus 1, and that's going to be the square root of 4, which is equal to positive 2. For the next one is a cubic function. And again, this is working in practicing following our order of operations. So we have this -1 that's being subtracted by 1, that's being raised to the third power plus 2. So again, we make sure we follow the order of operations here, that we are going to simplify inside the parentheses first and then raise it to the power. So -1 minus 1 is a -2. -2 cubed is -2 times -2 times -2, which is going to be a -2 times -2 is a positive 4, times a -2, which would be a -8, plus 2, which gives me a -6. The next one is the cube root. So remember, like the square root is saying, what number multiplied by itself, is going to give you a certain value. Well, the cube root is what number multiplied by itself 3 times, is going to give you that radicand answer. So let's just go ahead and plug it in. So we have 8 times -1. I'm going to close that, minus 2. All right, so -8 times -1 is a -8. A lot of people say, oh, you can't take the cube root. Well, remember, square root, you can't take the square root of a negative number, but the cube root you can, because -2 times -2 times -2, we just figured out, is -8, or sorry, is positive 8. Actually, I'm moving too fast. So therefore, this becomes the cube root of -8 minus 2. The cube root of -8 is going to be -2 minus 2, which is a -4. All right, so the next one is piecewise functions, and I know a lot of students have a really, really tough time working in with piecewise functions. So that is why, when I teach this, you actually spend a whole day going over piecewise functions because it's just one that students have a hard time, wrapping their head around. But without getting in too much depth here, if we want to evaluate this piecewise function for -1, we got to look at the constraints. This is we're only going to use x minus 1 for x values that are less than 0, and we're only going to use x plus 1 for x values that are greater than 0. Well, obviously, our x value that we're evaluating is less than 0, so therefore we're going to use this equation. So therefore, we're just going to plug in a -1 minus 1, and therefore we end up getting a -2. So f of -1, oops, I guess it's not really an expression, but f of -2 here is going to equal -2. So therefore you can see how plugging them in for those expressions. So this is important to find the value of the expression as well as working on some of those order of operations, as well as going back to some functions that we maybe have not spent as much time on, previously. All right, so the next one is solving quadratic equations by factoring. This is something obviously that is huge if you're going through the pre-calculus and kind of like calculus track. You see a lot of factoring come up, and a lot of students, have trouble with the factoring. So the intent of this video is not to kind of break down the factoring process. Obviously, I'll have more of those videos, available for those people that need it. This is really to kind of brush up on those factoring skills. So I will be doing factoring in my head. I will explain a little bit, where I'm getting those values, but, I don't want this, again, this is just a review of the factoring that we have already taught previous to pre-calculus. All right, so notice that they're all set equal to 0. These are all quadratics that we have set equal to 0. And I already told you that we're going to solve them by factoring, so we don't need to worry about using the quadratic formula or completing the square. These are all going to be factorable. And most of them are trinomials. We do have a couple binomials. So we will look into, using either the square root method or looking into square root method, or also looking into the difference of two squares. Oh, that would have been a good one. Yeah. All right, so let's go ahead and get into the first one. So again, if we want to look right into factoring, guys, we're looking into rewriting an expression as a product. So right here, basically, if you remember that a binomial times a binomial is going to equal it. When you multiply binomials together, you get a trinomial. So what that means is we can rewrite this as this is factorable. This trinomial can be rewritten as the product of two binomials. And remember, we can always check our work, right? Always check your work. So whenever I see a trinomial and I know that I want it to be factored, I'm going to break it up into the product of two binomials. And, I don't like to usually teach with the FOIL, but that's kind of an easy way to understand that, we know that the first two terms, x times x, if we were to follow distributive property or FOIL, x times x would give us x squared. Now we got to think about what two numbers are going to multiply to give us 2. Well, fairly easy. We only have 2 and 1, or -2 and -1. But what we have to do is look at, well, if we're going to multiply those two numbers, what are the only two numbers that multiply to give you 2, but then add to give you -3? So you're combining those two values to get -3, and you're multiplying to give you 2. Well, hopefully you recognize that the two values are going to be x minus 2 and x minus 1, right? And again, we can kind of check this. So x times x gives you x squared. I'm not going to do this for all of them, but I'll do it for this one. -2 times -1 is +2. And then you can see that -2 times x is -2x. And -1 times x is -x. So -2x plus x is going to equal -3x. And again, if you need more help, work it out. Multiply it all out, and you'll see once you simplify this, that gives you that trinomial. However, that's not really what we're asking here, is it? We're asking to solve. So once you have this set equal to 0, once you have it factored set equal to 0, you can apply the zero product property. And the zero product property basically states if you have the product equal to 0, then you can set each one of those factors equal to 0 and now solve. So here we have x equals 2 and x equals 1. All right. And again, if you want to check your work, plug them back in. You can check your work on factoring by multiplying it, make sure it goes back. And you can also check your solutions by taking your values, plugging them back into the equation, and you should get equal to 0. All right, so the next one, we're going to work a little bit faster. I'm looking at -4. What two numbers multiply to give you -4, but add to give you a -3? So that's going to be an x minus 4. I hate my 4s. And an x plus 1. Okay, again, I have my product equal to 0, so I'll go ahead and apply the 0 product property. All right, so therefore we have x is equal to 4 and x is equal to -1. All right, the next one is not a trinomial. So you could put a 0 there, but that'd be kind of weird. So let's look at some different factoring techniques. Well, the first factoring technique that I think we should always look for is just factoring out a GCF, the greatest common factor. And I didn't put this at first because, a lot of students get to this and then they struggle with the trinomials. So I wanted to do the trinomials first and then kind of work backwards. So let's factor out the GCF. The GCF here is an x. So we have x times x plus 5 is equal to 0. So again, we can apply the 0 product property. X equals 0, that's relatively simple. And then x plus 5 is equal to 0. So x equals -5. The next one, we can do the exact same thing here, but hopefully you recognize that this is a difference of two squares. And, doing the difference of two squares, a squared minus b squared equals a minus b times a plus b. So hopefully you recognize this factored form is x minus 2 times x plus 2 equals 0. It's called a special factoring technique. And therefore, we can just say, if you set these both equal to 0, x equals 2 and x equals -2. All right, so the next one is one that is going to get a lot of students because, they struggle with this, like how can I factor this? And you could do 1 minus x, 1 plus x, and that's perfectly fine. It does say to do this by factoring. Now, while doing 1 minus x, 1 plus x would work, there's nothing wrong with that. Typically, we like the variable, to be in front of the number. So I'm going to kind of show you a factoring technique, and then I'm also going to show you, another way we can do it. If we just needed to solve this, we didn't really need to factor this, we wouldn't really use factoring to do this. But my whole point here was really to get you guys to kind of prove your factoring skills. So the first thing I'd do is, if I needed to factor this, I would rewrite this as -x squared plus 1 equals 0. Then I would notice that they have I can factor out this -1. And if I factor out the -1, I get this as an x squared minus 1 equals 0. Now you can see this is a special difference of two squares again. So I can do x minus 1 times x plus 1. Okay, now the negative doesn't really impact my answers at all. I can just divide out that -1. It's not going to change any of my answers here. So therefore, I'll still just have x minus 1 equals 0 and, x plus 1 equals 0. So therefore, x would equal 1 and x would equal -1. So the negative, when you have something that's multiplied by your factors, but it's not actually, a variable, if it's just a number, in this case, -1, it doesn't impact your solutions. And that's important, and that's going to come up quite a bit in some of these other problems. The other way you could just simply do this problem, if factoring wasn't really what I asked you to do, you could just add the x squared to the other side, right? And then we could do what we call the square root method, just take the square root to both sides. The reason why that's important, though, remember, when you introduce the square root, you got to do plus or minus. So x equals plus or minus 1. A lot of people, they don't want to do factoring, so they do this method, and then they forget that the square root of 1, when they introduce that square root, is plus or minus. So you can see, by doing it the factoring technique, you can see how we get the plus or minus -1. So you can see, why that's kind of nice with the factoring not to make those mistakes. All right, the next one here is hopefully recognize, what two numbers multiply to give you 9 that add to give you 6. This is a special, again, another special factoring technique. This is what we call a perfect square trinomial, because the numbers that multiply to give you 9 and add to give you 6 are exactly the same. X plus 3 times x plus 3. So you can see that the solution is actually going to be repeated. You can rewrite it as, also x plus 3 squared, and then, take the square root if you like to. But either way, you see there's only one solution, x equals -3. It just gets repeated. And that's something that we're going to learn later, in the course from there. But it's just nice, important to see that this only gives us one solution. All right, let's get on to three more kind of trinomials. Again, we see this negative here. We don't really like the negative in front of our x squared, so I'm going to factor that out. So I get an x squared plus 7x plus 6 equals 0. All right, now I can just go ahead and factor this. What two numbers multiply to give me 6, add to give me 7. So again, I'll do an x plus 6 and an x plus 1. Okay, so then again, I have this negative, but you could divide out the negative like I did over here. But a lot of times when we're looking at solving, we just like drop it. We don't even do anything else. We're just like, it's not really there. It's not necessary. It's not doing anything for us. So I'm just going to kind of divide it out, but not show that. And just say we don't really need it anymore. It's not going to impact our solution. If you divide by -1 on both sides, you're still just going to get x plus 6 times x plus 1 equals 0. So then our solutions here is x equals -6 and x equals -1. All right, now we have some numbers in front of the x squared. So this is usually where a lot of students are going to have some trouble. Fortunately for this first one though, we recognize that every single term of our quadratic is divisible by 2. So that means I'm just going to factor out the x squared. And fortunately for me, when doing that, or you if you're doing these problems, that gives us another quadratic, which actually gives us a perfect square trinomial. So I'm just going to rewrite this as a 2x plus 2 squared equals 0. Now again, hopefully you see that this 2 is not impacting anything. Like you can just divide out the 2 on both sides. That multiplying that 2 in front does not change any of the answers, right? And if you were to take the square root of both sides, if you do it this way, again, you just get x plus 2 equals 0. There is no plus and minus of 0 because 0 is not positive or negative. So again, since this is a perfect square trinomial, you can see there's only one solution, x equals -2. All right, so now let's get on to the last one where everything is not divisible by 2. Hopefully, but you recognize with all the trinomials that I've worked on so far in this paper that any trinomial, if it's factorable, it's going to be rewritten as a product of two binomials. So I'm going to rewrite it as a product of two binomials equal to 0. So I know that the first two terms need to multiply to give me 2x squared. So I'm going to use 2x and x. My last two terms need to multiply to give me 2. Well, again, it's positive 2, positive 1, -2, and -1. Those are my options, right? But my middle term now needs to add up to 5x. So immediately in my head, I recognize if that needs to go to a positive 5x, I need to work with positive 2 and positive 1, right? I don't want to work with negative numbers and try to add them to give me a positive. That doesn't really make sense. I also need to get kind of close to 5. So I don't want to multiply 2 times 1 and 1 times 2. But if I do 2x, if I multiply that times 2, that gives me a 4x. And then if I multiply that by 1, that gives me 5x. And therefore, if I multiply this out in my head, hopefully by the end of this course or this chapter, you're going to start getting to that point. You can see that I did factor it correctly. So now I'm just going to set each one of my factors equal to 0 to apply the zero product property. And therefore, solving for x, I get x equals -1/2 and x equals -2. So factoring is a big portion. Hopefully, what you're going to notice is what these need to know that I'm going to be providing here. There's going to be a lot of factoring, and hopefully that's just going to build up your confidence as you get through the course, and that's not going to be something that's going to hold you back. The next one is solving and graphing the solution using a number line. And I really wanted to kind of do these just so you guys can really understand. We don't really deal with inequalities as much in the pre-calculus, but I like, working with this one for domain is this comes up quite a bit. And also just really kind of understanding, when equations are true, where is the solution true? And if you remember, solving inequalities was just like solving equations. You want to isolate your variable. And these are all relatively easy ones here. 2x minus 1 is greater than or equal to 5. So again, you could treat this just like an equation. Isolate this x, so we're going to use our inverse operations, kind of basic for us. But, either way, divide by 2, divide by 2. What happened there? Why did I not get a 6? 5 plus 1 is 6. So therefore, divide by 2. X is greater than or equal to 3. All right, so now we need to graph x is greater than or equal to 3. So what we're simply going to do here is just kind of create a nice little number line. I'm going to put 3 right in the middle, and I'm going to put 5 to the right and 1 to the left. All right, so numbers to the right are larger, numbers to the left are going to be smaller. And obviously we want x as our solution. It has to be greater than or equal to. So to represent the or equal to, we're going to make a nice little dot, and we're going to fill it in. And then if we want to represent all values that are larger than 3 or greater than 3, then we're just going to do shade to the right of the number 3 and then put an arrow, meaning that all the values continually going in that direction are always going to be larger than 3, and they're always going to be a solution to that inequality. The next one here, we have 5 minus 3x is greater than 4. So what we can do here is, again, using my inverse operations, I'm going to subtract a 5. Then I'm left with a negative 3x is greater than negative 1. Now I can divide by negative 3. And if you guys, remember, one of the things is, whenever you're multiplying or dividing by a negative to solve an inequality, you're going to want to flip the sign. And that isn't like a trick or anything like that. If you wanted to get around that, you could have simply just added 3x to the other side and then solve for the x in the positive form. So it's just the way that how it works out. Also notice that I have x is now less than 1/3. Now some people are like, well, how am I going to do a number line with 1/3? Well, just, you are the master of your number lines. So if it's not an integer, that's fine. Here's 1/3. Ooh, that was not supposed to happen though. Okay. Now, what about numbers that are like larger than 1/3 or whatever else? Well, let's just, let's do something that's not as evil. Let's say, all right, here's 1. Here's negative 1, right? So we obviously know more positive numbers to the right are going to be larger than 1/3, and negative numbers, to the left are going to be less than. Obviously, this is not to scale. It's just wanted there to representation here. X is less than, but it doesn't say equal to. So to represent that, we still need to show where we're starting. So we're going to use an open circle. And now what we're going to be doing is go ahead and using, sorry about that. And now we're going to be using the number line going to the left. Okay. And therefore you can see that how that works from there. Now this next one's kind of interesting. The quadratic inequality. X squared minus 1 is less than or equal to 0. So again, this one is a little bit interesting. I just wanted to kind of working with students, as far as x squared minus 1 less than or equal to 0, how do we really approach this? There are a couple different ways we can look at this. I think the best way to understand this conceptually is looking at what the graph would be. So if we had x squared minus 1, because for quadratics, remember when we were solving quadratics, a lot of times we got more than one answer. So I think it's easier to kind of understand when we're graphing a quadratic or an inequality or a quadratic inequality to understand what the graph looks like. So if I know x squared minus 1, and if I was to think about that equation, I could graph that equation. It's going to look something like this. Okay, now again, this says is for what values is x x squared minus 1 going to be less than or equal to 0? Well, here's the value of 0 right here. So when is it less than 0? Well, this value here is negative 1, and this value here is 1. So it looks like it's going to be less than or equal to 0 for all values when x is greater than or equal to negative 1, and when x is going to be less than or equal to positive 1. So you can see that it has to be between those two. You just can't say it has to be greater than negative 1 because it's really the intersection of those two, right? Another way you could write it be like negative 1 is less than or equal to x, which is less than or equal to 1. But it's just important. You don't want to use or. It's not like it has to be greater than negative 1 or less than 1 because over here is less than 1, right? But it's not, greater than negative 1. So it has to be that intersection domain. Now, obviously, you could get around this same part. You could also work with this algebraically, but you can see that's where some things kind of fall apart here. Less than or equal to 0, less than or equal to 1. And so therefore, when you now take the square root of both sides, you're going to get the positive 1. X is less than or equal to 1. But understanding how you get x is greater than or equal to negative 1 is the reason why we want to get through this. So the best way, at least to understand that, I believe, is to look at the graphical approach. All right, so we are almost done there, guys. Let's just go and look at simplifying expressions. And so we have a couple different ones, some polynomials, some radicals, as well as some rational expressions. So just remember, when working with expressions, or we're working with polynomial expressions, that we want to combine like terms. And combine like terms meaning that if you have a exponent, that they have the same base as well as the same power. So the 3 is what we call the coefficient. The coefficients don't need to be the same, but when you add like terms, you are going to be combining the coefficients. But our main thing is we need to have the same term. So x squared and x squared are the same term. They just have different different coefficients, but that's fine. These are like terms. This is not a like term. So therefore, this gives me 4x squared plus a 3x to the 4th. All right. Over here, we're basically just going to go ahead and multiply out. And it's important, this is where like FOIL kind of breaks down. So we want to make sure that we understand this using, distributive property. Every single term needs to be multiplied by every single term. All right. And sometimes you could use the box method, which is another thing that I teach. But we'll get into that more, once we get into the curriculum or, also next chapter. But let's do x times 3x squared is going to be a 3x cubed. X times negative 4x is a negative 4x squared. X times negative 5 is a negative 5x. Now in this case, what I'm going to do is I'm just going to add these two together. So I'm going to use what we call the vertical method. And I'm just going to take now negative 1 times 3x squared, and that's going to give me a negative 3x squared. I'm just going to put that down below because I'm going to add them vertically. You don't have to do it this way. This is just one method that we teach in the algebra 2, algebra 1. Negative 1 times negative 4 is going to give me a positive 4x. And negative 1 times 5 is going to be a positive 5. So now, as I combine these two together by adding them, I get 3x cubed. Negative 4x minus 3x is going to be a negative 7x squared. Negative 5x plus 4x is a negative x plus 5. All right, the next one, radicals. So same kind of thing with, polynomials, where they're with exponents. When you're combining them, they got to be like terms. What that means is the index of your radical, this little value here, if there's no number there, then we assume it's going to be the square root, or 2. So you have to have the same index as well as radicand. Remember, what's under the radical has to be the same. So this one's kind of tricky again because, again, we're looking at the number in front, 4 and 4. And a lot of people say, oh, well, they're the same. But those are the coefficients. Coefficients don't make like terms. It's the index and the radicand. So therefore, you can see that these two terms are like terms. So I'm going to just rewrite this by grouping them together. So therefore, I can easily see which ones are like terms and which ones are not. Okay, so 4 times the square root of 3x and 2 square root of 3x is going to be 6. Yeah. 6 times the square root of 3x. Notice when I'm combining the terms, I'm combining the coefficients, but leaving those terms the same. And then plus 4 times the square root of 2x. Just make sure those go over. Okay. The next one here is 5 times the square root of 3x. Remember multiplication. Just remember when you're multiplying radicals that you multiply the radicands inside and you keep the index in the same. And also if you have coefficients, you're going to multiply those. So in this case, I don't have anything to multiply the 5 by. However, in the radicands, I'm going to get a 9x squared. And then here, I can multiply the 5 times 2, so that's going to be a negative 10. And I can only multiply numbers times numbers, right? So that's 3 times 6 is going to be 18x. Yeah. Okay. Now, obviously, I can simplify this. The square root of 9. So now you can take the square root of individual values here. So the square root of 9 here is 3. The square root of x squared is x. minus 10. Square root of 18, we can actually break that up into the square root of 9 times 2. So that'd be times 3 times the square root of 2x. So we can't simplify that any further. So we're going to leave that just as. Therefore, we have 15x minus 30 square root of 2x. And again, we're going to have some common terms. I can see that these share a 15. So you didn't have to do this, but, you know, let's just add them in there. If I want to factor out my common term, 5 minus 2 comma 2x. Boom. So there's your two radicals. Now let's get into rational expressions. So dividing. Remember, dividing is the same thing as multiplying by the reciprocal. So this is not a fraction. So again, to turn anything to a fraction, just put it over 1. If you need to divide, then just go ahead and rewrite it as a product of the reciprocal. So just flip that divisor that you have. All right, now you can multiply. Remember to multiply straight across, not doing cross multiplying or anything. You could simplify it beforehand, but if you, you know, are a little bit not there yet, then don't worry. We can just rewrite this as x over 20x, and then the x's are going to divide out, and that's going to leave us with a 1/20th. Okay. The next thing that we're going to be working on is the fractions. Remember, when we're adding fractions with unlike terms, basically what we want to do is get a common denominator. So one denominator here, we have 3x. The other denominator, we have a 4x. So, you know, if we need them to be common denominators, we got to, you know, figure out the value, the denominator that they both were going to divide into. A quick and easy way to do that, it doesn't always work, but it's just to multiply 3x times 4x. And that's going to give us a 12x squared. But that doesn't give you the common denominator, right? Because we don't need to get a 2 squared. That's not the common denominator. The least common denominator is actually just a 12x, right? We don't need x squared. So to get to a 12x, I can just multiply by a 3 over 3 and a 4 over 4. Therefore, I get a 4 over 12x plus a 3 over 12x. Now, when multiplying rational expressions, remember we're just going to add the numerators and keep the denominator the same. So therefore, we get a 7 over 12x. All right, and last but not least, ladies and gentlemen, we have identify the transformations of the parent function. And basically, when we're doing this, you know, you can go ahead and play around with the graph. I just wanted to remind you of some things. You know, feel free to plug these into a graphing calculator or into Desmos online or into, you know, a Google browser and see what they look like. I'm just going to kind of run through the transformations. I'm not going to get too in depth, you know, with them because we spent some time on that. But I just wanted to identify the transformations here. This is going to be a shift up 2. When you're adding 2 inside of the function, though, that's going to have to be a shift to the left 2 units. And when we're not adding, so you notice how these two are adding. This is adding outside the function. That shifts the graph up. Here we're adding 2 inside the function. That's shifting the graph to the left. Here we're not adding 2. We're multiplying by 2. So what that does is that doesn't shift the graph at all. What that does is that actually stretches the graph. And since it's on the outside, that would be what we call a vertical stretch. And instead of saying it's vertically stretched, you know, 2, we're going to say a factor of 2. All right, ladies and gentlemen, so that is kind of it. You know, again, not a complete summary of everything you need to know to prepare you for functions in precalculus, but I think a pretty good list to at least get you started on some types of problems, some types of functions, some types of expressions, some types of processes that you are going to see in this upcoming chapter. And I really do feel that if you're able to, you know, work through these problems and feel pretty comfortable with the content that we went over, then you're going to do very well in the functions unit. So I look forward to being able to continue helping you with that content. And obviously, we will get started with that next. So there you go, guys. Hope you enjoyed. Cheers.